In this video, we're going to be reviewing kinematics for AP Physics 1. We're going to start with scalars and vectors. Scalars are quantities that have magnitude only. Examples of these are distance and speed. Vectors are quantities that have magnitude and directions. Examples of these are displacement and velocity. Distance is the total ground covered. So this would be your odometer reading in your car. Displacement is the change in position. We can calculate this using the equation delta x is equal to the final position minus the initial position. Speed is how fast an object is moving, and the equation for average speed is distance over time. You'll notice there's a bar above the s that just means average. Velocity includes both speed and direction, and the equation for average velocity is displacement over time. Now we're going to take a look at an example. Here we have a numbered line. Imagine that we start from 1 and we go to 3. Each of these numbers represents a position measured in meters. So our initial position is 1 meter and we go to 3 meters. And then from 3 meters, we go in the negative direction to negative 1 meter. So the distance is the total ground covered. We went to the right 2 meters and we went to the left 4 meters. So 2 plus 4 is 6 meters. The displacement only cares about your initial and final position. It doesn't matter how you got there. So our final position is negative 1. Our initial position is 1. So negative 1 minus 1 equals negative 2 meters. To find the average speed, we're going to take the distance divided by the time. Let's say that this travel took us 6 seconds. So the distance is 6, the time is 6. So 6 divided by 6 is 1 meter per second. To calculate the average velocity, we take the displacement divided by the time. The displacement is negative 2 meters. The time is 6 seconds, and we get negative 0.33 meters per second. Now we'll take a look at an example that's two-dimensional. Let's say we go 3 meters east and 4 meters north. What is the distance? What is the displacement? So the distance would be 3 plus 4, which is 7 meters. That's the total ground covered. But the displacement only cares about your initial and final position. So notice that this is a right triangle, so we can use Pythagorean theorem. A squared plus b squared equals c squared. So if we take 3 squared plus 4 squared is equal to 5 squared. So that displacement is going to be 5 meters. Let's say you were to go in a circle. What would your displacement be? Since displacement is final position minus initial position, you're back to where you started. The displacement would be 0. Now we'll take a look at acceleration. Acceleration is the rate at which velocity changes over time. And you know something is accelerating if the object is speeding up, slowing down, or changing direction. If the acceleration and the velocity are in the same direction, then the object is speeding up. If the acceleration and velocity are in opposite direction, then you know that the object is slowing down. The equation for average velocity is the change in velocity delta v divided by t. You can also write this as vf minus vi over t. The unit for acceleration is meters per second squared, or sometimes can be written as meters per second per second. If your acceleration was 3 meters per second squared, what that is saying is that every second the speed is changing by 3 meters per second. And now we're going to take a look at an acceleration problem. So here we have a car that starts off with an initial velocity of 5 meters per second and increases at a uniform rate to a velocity of 25 meters per second over a time period of 4 seconds. And we're going to calculate the acceleration using our equation, final velocity minus initial velocity divided by the time. We're going to substitute 25 for the final velocity, 5 for the initial, and 4 for the time. And we get 20 divided by 4, which is 5 meters per second squared. So if you take a look at this chart, it gives you an idea what 5 meters per second squared means. It means that every second the velocity is increasing by 5 meters per second. Now we're going to talk about motion graphs. On a position versus time graph, the steepness of the graph tells us the speed of the object. The slope of the graph tells us the velocity, and the velocity tells us not only how fast the object is moving, but also the direction. So it could be a positive slope, which means a positive velocity, or a negative slope, which means a negative velocity. On a velocity versus time graph, the slope represents the acceleration, and the area between the graph and the x-axis tells you the change in position or the displacement. Now this area could be positive, or the area could be negative, because you can have either a positive or negative displacement. On an acceleration versus time graph, the area between the graph and the x-axis represents the change in velocity. And once again, this could be a positive or a negative change in velocity. Now we'll take a look at some motion graphs. So on the first position versus time graph, you'll notice that we have this curved graph. To translate this to a velocity graph, we're going to look at the slope of the position graph. So you notice that at the beginning, there is a positive slope. So we know we're going to have a positive velocity. At the highest point of this position graph, you notice that it's flat. The slope of the tangent line is flat. And so the velocity is going to be 0. And at the end, the slope is negative. So we know we're going to have a negative velocity. Since we're dealing with constant acceleration, we know that the velocity graph is going to be a straight line. And in this case, it's slanted downward. Now, to translate this to an acceleration graph, we look at the slope on the velocity graph. Since it's slanted downward, this is a negative slope. So that means that the acceleration is going to be negative. Another way to represent motion is through motion maps, also known as dot diagrams. So we're using dots to represent the position of the object, and the distance between the dots tells us how fast the object is moving. And if the dots are getting closer, that means the object is slowing down. If the dots are getting further apart, that means the object is speeding up. And if you take a look at the position graph, you'll notice at the beginning the slope is getting less and less steep, and so we know it's slowing down and it's moving in the positive direction. So the dots are getting closer and closer in the positive direction. And then once it comes to a stop at an instant, it's going to turn around and it's going faster and faster, and so the dots are getting further and further apart. Here is another motion graph, and this one looks kind of like a U. At the beginning part of this graph, you'll notice that it has a negative slope, so the velocity is going to be negative. At the midpoint of this graph, it's a flat line. The slope of the tangent is a flat line, so the velocity is 0. And then at the end of the graph, it has a positive velocity, or positive slope, and so it has a positive velocity. So to find the acceleration, we're going to look at the velocity graph, and the velocity graph is slanted upward. It's a positive slope, so the acceleration is also going to be positive. Now, the area under the velocity graph tells us the displacement, and what you notice is that in this case, the displacement at the first half of the trip is equal to the displacement the second half of the trip, except the displacement the first half is negative, displacement in the second half is positive. And so if you wanted to find the total displacement of this object's motion, it would be 0 because the first half cancels out the second half. Now for the acceleration, the area under the curve is the change in velocity, and we have a positive change in velocity. So what's going on in this graph? So this object is going in the negative direction and slowing down to a stop, as you can see in the motion map, and then it turns around and it speeds up in the positive direction. So it's going the negative direction, slowing down to a stop, and then turns around and speeds up in the positive direction. Now we'll take a look at the kinematic equations. On the equation sheet, you'll see the first 3, but the fourth one can be helpful, but it's not on the equation sheet. So let's go through the variables, make sure that you know what each of the variables are. So delta x is displacement, vi is the initial velocity, vf is the final velocity, a is acceleration, and t is time. You'll notice that for each equation, it has 4 variables. There are 5 possible variables, but each equation has 4 variables. And this equation chart is helpful to help us to figure out which equation to use. So when you're solving a problem, you want to write down all the variables that you're given and look at the variable that you're not using. And we're going to use that variable that you're not using as a clue to figure out which equation to use. So for example, if you're solving a problem and and displacement, delta x, is not involved in the problem, then you would use VF equals VI plus AT. So now let's work out a kinematics equation problem. We have a car that's initially moving at 30 meters per second and slows down to a stop. And we're going to make right positive. The acceleration is -4 meters per second squared. We want to know the horizontal displacement. How far does it travel? So we're going to start with our variables chart, delta x, VI, VF, AT. And we know that VI is 30 meters per second, VF, our final velocity, is 0, and the acceleration is -4 meters per second. And we're looking for the displacement, so we're going to put a question mark there. And notice that t is not involved in this problem solving, so that's our clue to figure out which equation to use. So I'm going to go back to my chart and look at t, and then go down from where t is. We'll see that shaded in section and go to the left. We see our equation, VF squared equals VI squared plus 2a delta x. And so we're going to use that equation. So we're going to substitute our known variables and solve for the unknown for delta x, and we get 112.5 meters. Next, we're going to take a look at free fall. So when an object is in free fall, it means that it's falling only under the influence of gravity. And the acceleration due to gravity is approximately 10 meters per second squared. It's going to be downward. The more precise number is 9.81, but on the AP Physics 1 exam, 10 meters per second squared is accepted. So let's start with a ball that's dropping from rest. We're going to use a motion map to represent this motion. As it's falling, it's going faster and faster. So you notice that the dots are getting farther and farther apart. At 1 second, the velocity is 10 meters per second. At 2 seconds, 2 seconds, the velocity is 20 meters per second. At 3 seconds, the velocity is 30 meters per second. So when we say that the acceleration is 10 meters per second squared, what we're saying is that every second, the speed here is increasing by 10 meters per second. Now, what if we threw a ball up, straight up? Okay, so a ball straight up and then coming back down. We're going to make up positive. And so as the ball is going up, it's going to have a positive velocity. So we're going to start off with 30 meters per second. 1 second later, it'll be 20 meters per second. 2 seconds later, it'll be 10 meters per second. 3 seconds later, it'll be at its peak height with 0 velocity. And then it's going to come back down. 1 second later, it'll be -10 meters per second. Another second later, it'll be -20 meters per second. And then another second later, it'll be -30 meters per second. Now we're going to solve a free fall problem where we throw a ball straight up into the air with the initial velocity of 20 meters per second. We're going to make up positive, and we want to find out what is the final velocity once the ball is 10 meters above the thrower's hand before it reaches the peak. So we're going to start with our variables chart, delta x, VI, VF, A, and T. The delta x displacement is 10 meters, VI is 20 meters per second. The final velocity is what we're looking for, so I'm going to put a question mark. The acceleration is -10 meters per second squared because I made up positive, and so the acceleration is downward, so it's going to be a negative number. We're going to find an equation that does not have t, and once again, that's going to be VF squared equals VI squared plus 2a delta y. We're going to substitute the known variables and solve for the unknown VF. Don't forget to square root because VF is squared, and we get that VF is equal to 14.1 meters per second. Next, we're going to take a look at projectile motion. So while free fall motion is dealing with one-dimensional motion up and down, projectile motion is dealing with 2 dimensions. It's not only moving up and down, but also left and right. For the horizontal motion, the acceleration is equal to 0. There's no acceleration, and so it has constant velocity. So for horizontal motion, we'll be using the equation delta x equals vt. And for the vertical motion, the acceleration is 10 meters per second squared down, and this is because gravity force is pulling it down. We'll talk about that later in dynamics. And so for vertical motion, you'll be using one of the kinematic equations to solve for the vertical motion. Now, before we actually look at a sample problem, I just want to quickly review SOHCAHTOA. You'll need to know these trig ratios to solve projectile motion problems where we have an object launched at an angle. So SOHCAHTOA is a mnemonic to help us remember these trig ratios. Sine theta is equal to opposite over hypotenuse. Cosine theta is equal to adjacent over hypotenuse. Tan theta is equal to opposite over adjacent. Also, the Pythagorean theorem will be useful to solve these projectile motion problems. And so just a quick review that a squared plus b squared is equal to c squared for right triangles. And now let's take a look at motion maps for projectile motion problems. So we have a cliff here, and we're launching a ball off the cliff horizontally. So this is a horizontally launched projectile motion. And so what you'll notice is that horizontally, the arrows have the same length, which tells you that the magnitude of the velocity horizontally is constant. So it has a constant horizontal velocity, but vertically, it's accelerating, so you can see that the green arrows are getting longer and longer. If the object is launched at an angle, the horizontal motion is also going to be constant velocity, while the vertical motion, vertical velocity is going to be accelerating. On its way up, the vertical velocity decreases all the way up to the peak where it has 0 vertical velocity. And then as it's coming down, the vertical velocity increases downward. Notice that the peak, although there's no vertical velocity, there is still a horizontal velocity. So it is still moving the rightwards at the highest point. To find the speed at any point, you can combine the horizontal velocity and the vertical velocity using vector addition, as you see in the white arrow at the beginning of this projectile motion and at the end of the projectile motion. Now we're going to solve a projectile launched at an angle problem. Here we have a ball that we're kicking at an angle, and the ball is getting kicked at a speed of 15 meters per second at an angle of 30 degrees above the horizontal. We want to first calculate the initial velocity, the initial horizontal velocity, and the initial vertical velocity. So we need to do a little bit of trig. To find the vertical initial velocity, we're going to use sine, because sine is opposite over hypotenuse, and the opposite is Vy, and the hypotenuse is 15. Multiplying 15 on both sides gives us 15 sine 30, and we get 7.5 meters per second. To find the horizontal initial velocity, we're going to use cosine, which is adjacent over hypotenuse. The adjacent is Vx, the hypotenuse is 15, so Vx is equal to 15 cosine 30, which we get 13 meters per second. For part B, we're going to calculate the time that the ball is in the air, the flight time. And so we're going to create this chart here that has both a horizontal column and a vertical column. And we know that the initial velocity horizontally is 13 meters per second. We just calculated that. The final velocity will also be 13 meters per second because horizontally it's moving at constant velocity. The vertical initial velocity is 7.5 meters per second, which we just calculated. The acceleration is 0 because horizontally the object is not accelerating. For the acceleration vertically, we're going to set right positive in the x direction, and the y is going to be positive going up. And so with those positive directions, the acceleration will be negative 10 meters per second squared vertically because we made a positive, and we know that the acceleration due to gravity is down. Now, our strategy for finding the flight time is to find the time to get to the peak height and then times 2, and then that will give you also the time to go all the way to the top and then all the way back down. So to find the time to get to the peak height, we know that the peak height, the velocity, the final velocity will be 0. So now we need to find an equation that has initial velocity, final velocity, and acceleration, but it does not have, and we're looking for time, but it doesn't have delta x. So that equation would be Vf equals Vi plus At. And substituting what we know, we get that t is equal to 0.75 seconds. Remember, this is half of the trip. It's from the ground to the highest point, but then it also needs to come back down to get the flight time. And so we take 0.75 times 2, and we get 1.5 seconds. For part C, we're looking for the maximum height. What is the peak height? What is that distance? So we're going to use Vf squared equals Vi squared plus 2a delta y. We're going to substitute our known variables and solve for delta y, which we get 2.81 meters. Lastly, we're looking for delta x, the horizontal displacement, also known as the range. Because horizontally, the object is moving at constant velocity, we can use delta x equals vt. Horizontally, we know that the velocity is 13 meters per second, and the time is 1.5. Notice that the vertical time and the horizontal time is equal to each other as long as you're looking at the same part of the motion. And so delta x equals vt, we get 13 times 0.15, which gives us 19.5 meters. Next, we're going to take a look at relative motion. So motion is relative depending on your frame of reference, and sometimes frame of references are also moving, so we need a way to be able to solve these problems. The equation we're going to use is VAC is equal to VAB plus VBC. Let's take a look at the subscripts. Notice that it says AC and then it's AB, BC. Notice that the B's are next to each other and that the A is at the beginning, C is at the end. Keep this pattern in mind. We'll be using that to solve these problems. VAC stands for velocity of object A relative to object C. VAB is the velocity of object A relative to object B, and VBC is the velocity of object B relative to object C. In our problem, we have car A, which is traveling at 20 meters per second with respect to the ground, and car B, which is traveling at 25 meters per second with respect to the ground. And we want to know what is the velocity of car B with respect to A. So our subscript here is BA. So on the right-hand side, B is going to be in the beginning, A is going to be at the end, and the G is going to be in the middle. So we're going to write VBG plus VGA. VBG we know is 25 meters per second. But we don't have VGA. We have VAG. To switch those subscripts to VGA, we're going to flip the direction of the velocity. So instead of positive 20 meters per second, we're going to use a minus 20 meters per second. So we get 25 minus 20, we get 5 meters per second. So the velocity of car B with respect to A is going to be a positive 5 meters per second. Now we have a person in a train. The person in the train is moving to the right at 5 meters per second, but the train is also moving to the right at 20 meters per second. So the velocity of the person with respect to the train is 5 meters per second. The velocity of the train with respect to the ground is 20 meters per second. And we want to know what is the velocity of the person with respect to the ground. So the subscript on the right-hand side should start with the P, should end with a G. The train will be in the middle. So we have VPT plus VTG. VPT is the velocity of person with respect to the train, that's 5 meters per second. VTG is the velocity of the train with respect to the ground, and that's 20 meters per second. So 5 plus 20, and we get 25 meters per second.